Hi, my name's Case. I'll be doing part of the first one. So in the problem, we have like this wooden structure that's cut by a simple scarf splice here, and it's angled about 60 degrees.
Does it matter, like, the material, like, of it?
I think so.
Okay.
I mean, we're not like getting.
Yeah,
I mean,
there's no friction.
We're given the values. If you're like,
Yeah,
if you don't
gotcha.
know material, you might need to do some tests to like find these values. But
Okay.
luckily, we're given the maximum tensile value.
So theoretically, the material would affect that, but not like.
I think theoretically, yes.
Yeah.
It would.
But we don't need to take into account like the
Also
different
the size and
yeah.
like the density. I guess the material
okay.
properties.
Yeah, that makes sense.
Heavily affect it.
We'll get there eventually, I'm sure.
Yeah, but for now it's simple scarf splice with a 77 value for sigma, and we're solving for the maximum P, so we get the maximum tensile strength, and we also are given the area. It's a 3x5 cross section here, and we're given this equation which Andrew will help derive, but if you plug in your values, you do get
so
about
this is from the
1.54 kips.
textbook. I
Yeah,
think.
this was from the textbook. This is what I used.
Mm-hmm.
Andrew had a different approach.
Yeah.
What did you use?
So, I think she went over this. I'm gonna go over here actually. My bad. Oh my god. Okay, there we go. She went over this. This is kind of what we did in class, but if you just memorize this equation, obviously that's going to simplify it a lot. But if you want to just go ahead and kind of think about the bulk of the equation is just going to be sigma equals n over a. So that's kind of the simple equation, which can be applied to like a variety of different versions of problems. And then using this, I guess this is a free body diagram, we can go ahead and derive the same equation, and you're going to get the same answer. So what we go ahead and do here is we're going to have our normal force and then the shearing force. And since we know that we're solving for the stress, right?
Yeah, it's the maximum allowable.
Yeah.
P.
Yeah.
I think.
So
the largest load peak that can safely be supported.
Mm-hmm. And what the sigma is the stress, correct?
Yes,
that they gave us,
which is given.
Yes. So since we have this, we can go ahead and relate n in terms of p with our free body diagram here, which is just going to be a delta f. I guess this would be y. My drawing's not consistent with my work, but so delta fy or sigma fy, or what's that? I can't think of the.
Delta. Sigma Fy.
Sigma.
Some of the forces.
Yeah. You know what I'm doing. This is basic statics. We can get n in terms of p, and then go ahead and plug that in right here.
So we don't use V at all for this?
No. All you need is, I'm sure you'll have that for another. There could be
Okay.
another question like that, but yeah. So for now, we're just going to use n in terms of p, which is 0.87, which is the cosine component. And then we can go ahead and plug in for the area. So this is just the cross-sectional area. So in here, you used A naught, which we're representing as like this area.
Yeah, the top area.
So this is A naught. And then
so for your method, you use the theta?
Yes.
Oh, I see.
So that area is what we're going to call A theta.
It's a nice diagram.
Thank you.
So do we have like similar approaches, but mine kind of shifts to the A naught while yours uses the inclined kind of
Exactly.
approach? Okay,
That's good. Yeah. So this is like a derived equation.
I
but
guess this accounts for the incline, while yours
Yes.
is like the area in terms of the incline.
So here you can see where we get that. We have the A theta right here is going to equal A naught cosine over cosine theta, and so then we can go ahead and plug that in for A, and then you'll then set it equal to the maximum allowable, and you get our nice little answer.
So when you derive it, n equals p cosine theta, and A theta equals that. So when you plug it in,
you end up getting this equation.
Oh, so this is like the derivation.
I
That is
have a question about this part.
Yes.
Thomas Brandt asked a question. So
I give that credit.
I ran these numbers with my calculator, and I think this is the reason why I'm asking is because I kept getting this one wrong, and I think this is why. I got like I think it was pretty much this, but to like
Did you get
a factor of
0.2?
like 1,000 more or whatever. Do you know what the standard unit is? And is kips not the standard here in these? this
Well, if
problem?
you
Is
got
it,
1,000
it's because we were given it in PSI.
You did it in pounds, I think, and then you get to convert it back to
yes,
kips.
yeah.
So you divide by
Typically,
1,000.
typically, I think kips is standard though.
Yeah,
Yeah.
because there's such big numbers. They don't want to say like 20,000 pounds. They say
Exactly.
20 kips.
That makes sense.
Yeah, yeah.
Or, thank you.
Yeah, the PSI. Yeah. So anyway, so this is the applied formula that if you memorize this, obviously it's going to make this specific problem easier, but that's very niche formula. So if you want to memorize the general, you can just go ahead and use this and then do a free body diagram and move on from there. So this makes a little bit more sense to me, but if you just memorize this, it'll be easier. But anyways, okay, should we move on to number 2?
Hello, I'm Evan. For question 2, it's the second part to the first question, but this time we're looking for the shearing force on the object. And so it's a fairly similar equation where we've got the ratio of the load over the area, but instead of cosine squared theta, it's sine theta times cosine theta. And we don't have to like isolate any new terms, it's just set up perfectly for us.
Sorry,
Let's keep it down in the back, please. Thank you.
So we're going to use the load value that we got from part 1. What's up?
Do we have a question back there?
Yeah, I was wondering how you got that equation. Sorry.
Oh, it's given in the textbook.
No. We don't take that for an answer. I was about to explain what my colleague missed here.
Thank you, Thomas.
So the standard tau equation here that we all know and love.
This is kind of the same setup as before.
Very
Like we're gonna have
similar.
one equation that works, but it's
like-
not.
it's just-
There's a way
Yes.
to derive it.
yeah, there's a way to
So we have
derive
V
it.
over A. You might be asking, how do I get here to here?
I'm
Let
really
me show
wondering
you.
that.
Let me show you. All right?
So again, this is like the general formula right here.
General formula.
Yeah, which is I think more useful and more applicable in a lot of variety of problems. Versus this is like extremely niche.
Now, intuitively from our diagram, we can kind of derive that V will become, similarly to how we derived what F would be, V will be P sine theta. And then, now looking at this, you're like, okay, P sine theta over A is not the same as that. Another important thing to do here is what our A means exactly. So in this problem, it's important to differentiate A0 versus A theta.
So that's referring to. Well, technically for this formula, we want the cross section, so we want A theta.
Yes,
So we
exactly.
don't-
So we'll use this equation that
Yeah.
Andrew kindly provided,
Yes.
and we will get P sine theta over, what is this, A0 over cosine theta, which is equal to,
You derived this? Like, that's crazy.
what he wrote here.
Wow.
It's that
You
easy.
derived the whole equation. And then all we gotta do from there
Continue.
is plug in our values. Pretty simple. We just have the 10 times 10 to the third to convert for the kilo pounds to regular pounds. Everything else goes the same. You get 44.
What is this unit? That's also in kips?
I don't.
So that doesn't have any units, unitless.
Oh, that's
I think.
our
No,
final
I
answer is
don't-
PSI.
I think it's PSI.
Oh, it's
It should be
PSI.
PSI.
That's not,
Wait, real quick. How do we derive A naught and A theta?
It's a good
Yeah.
question. It's a good question.
So,
So, You-
please.
no. If you
Professor Thompson.
If anyone can answer it though.
okay. So here, let's go to this nice drawing. This is actually Thomas's drawing. I'll credit.
Thank you.
It's a very
So
nice
we're gonna call A naught is our original cross sectional area of just the uniform beam. Is this a beam, whatever you call it? And then A theta is going to be the cross sectional area of the actual splicing. So it's that angled area. So,
No, you could.
Brosan, can I get a marker?
Yes.
Please? Thank you. Beautiful. So if we're looking at it from the side, so this would be kind of like right here. So this is from the side view. So this is
the
our
60?
This is the splice. Yeah. So our 60 is right here, and then this would be our 30. So we have this is going to be the area of a knot, and then this is going to be a theta.
This is the simple scarf splice.
Oh, that's the splice. I
yeah,
see.
yeah. So this is the spliced side right here.
Ah, I see.
So that's like
Yeah.
right here.
Mm-hmm.
So we're looking at it from that view.
Yeah, yeah,
And
yeah,
then
yeah.
you can just go ahead and say, okay, so
Oh, I see. I see it now. It's
cosines
forming.
30 is
And this is this 90 degrees here? Wait,
That is.
Yeah,
Because he made a triangle here.
that's how triangles work. Yeah, my
60,
bad.
30.
That was
No, you're
dumb.
good. You're good. Good
Yeah.
question. And then you can rearrange the solve for A naught, which
And then yeah, there you go.
and A theta.
Yeah.
Good question.
Thank you.
Oh,
That
I
was-
That was a
good
good
explanation. Good explanation.
That was Case Rowan that asked.
Yeah, I did ask that question.
Okay. Yeah. Do we have any other?
Yeah, I've got to, because we've introduced like shear and normal forces.
Yeah.
No, you're good.
Oh, okay. So with this problem in particular, so a shear force is parallel to a surface, correct? A normal force is perpendicular.
Yes. So
In
the
the diagram
shear-
right there, you can
And
see.
so-
Thank you. Yeah. So
Divided
the
by
shear is a V,
That-
and then the normal is.
And the
normal.
load is like totally unrelated. That's simply just a force that we put onto it. That's
The what now?
like
The load is like
yeah,
an
P-
external
yeah,
force.
So yeah, P is
These
just
are
the
internal
applied.
forces.
like-
totally unrelated.
Yeah.
Okay.
External versus internal force.
So that's why
Very
we're saying like they're giving us the maximum. Do we have the units of this? Would that be in pounds?
That's PSI.
That's PSI. Okay, thank you.
Yeah.
So they're giving us the maximum pressure per square inch that we can have on this piece without its failure, and then so now we're trying to derive what the actual applied force is going to be given that that stress.
Cool.
Yeah.
All right, I think
think
that
that's
about
it.
sums it up. Thank you
All
very
right, thank
much.
you.